There are specific gases and particles that alter the Earth's energy balance, driving climate change. These include the greenhouse gases that we covered in a previous lecture that traps heats, and aerosols, which often reflect solar radiation and cool the climate. Let's break down the major contributors, their source, characteristics, and relative impact. Starting with greenhouse gas, it absorbs and re-radiates infrared radiation, enhancing the greenhouse effect. The primary greenhouse gases include carbon dioxide, methane, nitrous oxide, halocarbons, and water vapor. Starting with carbon dioxide, its main anthropogenic source is fossil fuel combustion, land use change, and deforestation. Its contribution to warming accounts for approximately 65% of anthropogenic radioactive forcing. Its atmospheric lifetime is up to 500 years or more. Importantly, carbon dioxide is the reference gas for comparing with others, so its global warming potential is 1. This is a concept we'll cover later on. Moving on to methane, its sources are agriculture, especially livestock, landfills, and oil and gas production. Its heat trapping potential is about 28 times that of carbon dioxide over a 100-year period, with a lifetime of roughly 12 years. So therefore, despite its shorter lifetime, methane has a disproportionately large near-term warming effect. Moving to nitrous oxide, its main sources are agricultural soils, such as from fertilizers, fossil fuel combustion, and industrial processes. Its global warming potential is 265 times that of carbon dioxide, with a lifetime of approximately 120 years. Halocarbons are sourced from industrial applications such as refrigeration and air conditioning. Its global warming potential can exceed thousands of times that of carbon dioxide, with a lifetime that varies widely from years to millions of years. Moving to water vapor, or what we call H2O, is the most abundant greenhouse gas, but not directly emitted by human activity. This is important. It acts as a feedback, not forcing. Warmer air holds more moisture, which amplifies warming. Therefore, it has an amplification effect. Alright, let's move to aerosols. In contrast to greenhouse gases, aerosols are tiny particles suspended in the atmosphere. They generally have a cooling effect, but contributes to atmospheric complexity. The first one we'll cover is sulfate aerosols. Its sources are combustion of fossil fuels with sulfur impurities. The effect is that it reflects incoming sunlight, contributing to a negative radioactive forcing. So let's visualize this. The energy will come from the sun arriving into the Earth's atmosphere. The aerosols would then act as a mirror, reflecting that energy back, therefore having a cooling effect, as some of the energy will not have reached the Earth's surface. In more correct terms, we can say the effect is reflecting incoming sunlight, contributing to negative radioactive forcing. The second aerosol we'll talk about is black carbon. Its sources is incomplete combustion from diesel engines or biomass burning. What you need to know about this aerosol is that it absorbs heat in the atmosphere and reduces surface albedo when on snow, therefore contributing to warming. The last aerosol we'll cover is mineral dust. The sources are agriculture, land degradation, and desertification. The effect is mixed. It can reflect or absorb sunlight depending on the compositions. Although aerosols typically have a shorter atmospheric lifetime from days to weeks, they play a significant role in regional climate dynamics and cloud formation. A concept that I mentioned we will cover later is global warming potential and atmospheric lifetime. These two metrics are used to compare greenhouse gases. Global warming potential is the amount of heat a gas traps over a specific time relative to carbon dioxide. So carbon dioxide is our reference greenhouse gas. And atmospheric lifetime explains how long a gas remains in the atmosphere. Let's try a sample exam question. So an analyst is reviewing two gases, one with an atmospheric lifetime of over 100 years and a global warming potential of 265, and another with a lifetime of 12 years but a global warming potential of 28. What are the gases and which contributes more to near-term warming? So this is a memory game, but also tests your understanding of the two concepts. The correct answer is B. The gases are methane and nitrous oxide. While nitrous oxide has a greater long-term impact, methane contributes more to near-term warming due to its potency and rapid energy absorption in the short term. Understanding the composition and behavior of greenhouse gases and aerosols is central to climate risk assessments and mitigation planning. So for the exam, you should be able to identify key gases and their anthropogenic sources, compare their contributions using global warming potential and atmospheric lifetime, and differentiate between warming and cooling agents, including short-lived aerosols. These concepts often appear in questions involving emission scenarios, policy choices, or sectoral risk assessments, so ensure you can apply them with both precision and clarity.